Hello, and welcome to Astronomy 100. In our previous segment, we were talking about blackbody radiation and how an object with blackbody behavior emits light in a particular way, reflects light in a particular way, and absorbs light in a particular way. And so what we're going to do in this segment is we're going to talk about how this concept of blackbody can lead us to the ability to determine the temperature of an object based on the light that it emits. So let's start with the idea of something very hot. In this case, we're going to use a piece of metal that had been just brought out of the fire. It's glowing, obviously red hot in its appearance. Imagine if we could take the light that comes from this piece of metal and we can pass that light through a prism. Now remember, the purpose of a prism is to take something that's all put together and to sort it out into its component colors. And in this case, the piece of metal that is glowing red hot, although it looks red to the eye, this is actually a source of white light. If you remember from a previous segment, anything that produces all of the colors of the visible spectrum is actually a source of white light. Now, to prove this to you, what I'm going to show you is essentially what you would see if you had the ability to take a photograph of all of the colors coming through the prism, ultimately coming from this piece of metal. What you would get is a rainbow, if you will, or a spectrum that looks like this. Now you'll notice that the colors, red, orange, yellow, green, blue, and violet, are all present. Admittedly, some of the colors are very faint. The violet is just almost imperceptible, but it's there. And then the red, of course, is very dominant. So if you recall, the definition of white light also had the important caveat that you do not have to have all colors equally represented. So this piece of metal is obviously producing a lot of red, and then of course not so much when it comes to the blues and the violets. Now what we want to do is we want to quantify the brightness of each of these colors. In other words, we want to know how bright is the red, how bright is the orange, yellow, green, blue, and violet as a number, rather than what you see with your eyes here. So the way that we do that is we allow an instrument to tell us the actual brightness of each of the colors as a number. And when we actually determine the number that represents the brightness of each of these colors, what we can do is produce it in the form of a graph. And so when you look at this graph, what I want you to sort of visualize is along the horizontal axis, we have a variety of wavelengths going from 4,000 angstroms all the way to 7,000 angstroms. Remember that 4,000 is the wavelength for violet and 7,000 is the wavelength for red. And the vertical axis of this graph is brightness. So what you see here is the red is the brightness all the way up to here. This is the brightness of the red as a number would represent it. A very tall size means a big number. And then all the way down here, the yellow doesn't quite go so high, so it is not as bright. Its number would be smaller. And then of course the violet is not very bright at all, so its number is very small. So you notice that if we were to graph it a series of numbers of brightness, number meaning brightness, over the wavelength, what you end up getting is a graph that looks like this. Very low down here and very tall up here, but notice that it also continues as we go towards longer wavelengths. Now this graph, if we were to instead show it like this, is what we call a blackbody curve. Meaning when an object has the behavior of blackbody and we measure the amount of energy or the brightness of each wavelength, what we do is we have a blackbody curve that is a graphical representation of how the brightness of each color is shown from this particular object. So what's really critical is this white line right here, in other words, what we call a blackbody curve. So this is the blackbody curve that comes from the light that comes from this object here on the left. Now, when we do this for various objects, it tells us information about the object itself. For instance, what I want you to notice is how even though the red stops right here, to your eye you can't see anything that is a longer wavelength than red, This blackbody curve demonstrates that there is still light coming from this piece of metal, but it's light that we cannot see with our eyes. If you recall, this part of the spectrum just beyond the red is in the infrared. So this piece of metal is producing infrared light, but it's light we don't see with our eyes, so there's nothing that we can show you here. So it produces most of its energy, most of the light coming from this piece of metal is in the realm of the infrared. So this actually shows us how much energy, or the brightness I should say, over each particular color. What do we do with the blackbody curve? Well, this is the important transitional part. What we're going to do is show you how the energy that is produced over all wavelengths that comes from an object with blackbody behavior can be turned into knowledge about the temperature of the body. So let me show you an example. This is a blackbody curve for an object in nature. What I want you to notice is how the curve becomes higher and higher and higher, has a peak, and then drops off. We could start either direction, it doesn't matter. Higher and higher with a peak, and then it drops off. To remind you of a couple of important things, remember that this is over various wavelengths, and remember that wavelength is color. And when we have wavelengths that are long, such as 7,000, it is red. When we have wavelengths that are short, such as 4,000, this is in the violet. So we have the numbers, we have the visual representation of those numbers, and we have the names to go with it, just to make sure that you understand completely what's going on the horizontal axis. Now, what I want you to notice is this is an object that is producing every color of the visible spectrum. For instance, there's this much red, and then there's this much orange, and there's this much yellow and green, and then this much blue, and this much violet. So it is producing every single color, but notice how it is not producing all colors equally. It is producing only this much violet, all the way up here, this much green, and then only this much red. So it is a source of white light. It is not producing all colors equally, but it is producing all colors. This is the blackbody curve of the sun. So if we would take the light from the sun, pass it through a prism, and get the individual colors sorted out, and then measure the brightness of each color, then what we would get is the blackbody curve that you see here. So quite obviously, the sun produces every color of the visible spectrum, but it does not produce all colors equally. And you may be surprised to know that the sun produces more green than any other color. So the sun produces more green than all the other colors of the rainbow. Now, what we also want, and here's the part that makes it so we can quantify, is we want to know where is this peak when it comes to wavelength. So what we're going to do is we're going to call this the curve maximum. In other words, this part right here is the peak of the blackbody curve. What we're going to then do is drop straight down, because what we want is a number that represents the curve maximum. So we want to know what is the wavelength that is represented, or I should say is representing the peak of this blackbody curve. So an example is, we could say from this graph that our sun produces most of its light at a wavelength of, oh, I don't know, 5,300 angstroms here. So the sun produces more green at this wavelength than any other color. Now we're going to give this a name. This exact wavelength we're going to call lambda max. This is the letter, or the Greek letter lambda. If you recall, that means wavelength. So lambda max means the wavelength of maximum brightness coming from, in this case, the sun. So what we would say is the sun's lambda max equals 5,300 angstroms. Now keep that in mind. It was in the latter part of the 19th century, it was towards just the last couple of years of the 19th century, when a German scientist by the name of Wilhelm Wien discovered that a blackbody curve has a particular way that it changes based on the temperature of the object producing the light. So here's what I'll show you. Let's imagine that we have an object. The object has a temperature of 3,500 kelvins, so quite hot, very, very hot. This is the blackbody curve that goes with the temperature 3,500 kelvins. Notice the peak of the blackbody curve is right here, not quite in the red, almost in the this part of the infrared. If we were to put a number, we would say lambda max is right here, and lambda max is, oh, I don't know, 8,000 angstroms. Now, here's what Wien discovered. Watch what happens when the temperature of the object changes. So if the object were to go from 3,500 kelvins to 4,500 kelvins, notice how the peak of the blackbody curve is now right here, whereas it was previously right here. So when we go from 3,500 to 4,500, the blackbody curve peak shifts towards shorter wavelengths. And now let's go one more step forward. If we were to go to 5,000, making the object even hotter, notice that the blackbody curve has shifted to an even shorter wavelength. One more step, if we were to go to 5,500 kelvins, notice that the blackbody curve has shifted even more. Now, I know that you probably have noticed that the peak of the blackbody curve has also risen as the temperature goes up, but for now we can ignore that. What's critical to see is that as the temperature of the object increases, the blackbody curve wavelength of maximum right here is shifting. Shifting to there, shifting to there, shifting to there. So Wien discovered that the peak of the blackbody curve, or lambda max, is dependent on the temperature of the object. And what I want you to notice is the dependence between the temperature and the peak and the wavelength that goes along with that peak is inverse. Let me go back and show you what I mean. Notice that the temperature is rising, becoming larger, but the blackbody curve lambda max is shifting to shorter wavelengths. The higher the temperature of the object, the shorter and shorter lambda max becomes. So we call this Wien's law. And Wien's law says that the wavelength where the object's energy reaches a maximum in its brightness is inverse to the temperature of the body. Notice the T is in the bottom, so if T becomes larger, lambda max becomes smaller. Objects that are hotter are going to produce their energy and their light with a lambda max that's at a shorter wavelength. Now, the problem with this formula, though, is that this assumes that you already know the temperature. What we want in astronomy is to already know lambda max and calculate temperature. So all we're going to do is we're going to turn it around, and you'll notice by doing just a little bit of algebra, doing an algebraic manipulation, we can convert the formula to this one down on the bottom. And this is the one that astronomers want: the ability to observe the light from an object, determine lambda max, and then calculate the temperature of the body. As a final example, let's put this into practice with the sun. We take the light from the sun, we pass the light from the sun through a prism, that light gets spread out into its colors, and from those colors, we determine a blackbody curve. From the blackbody curve, we determine lambda max, which is the wavelength where the curve reaches its maximum. Lambda max equals 5,000 angstroms. And then what we do is put that into the formula for Wien's law. And when you plug in 5,000, divide it into the constant, you calculate a temperature of 5,800 kelvins. So the temperature of the sun is 5,800 kelvins. And we know this because of the light that the sun produces. It produces the light the way that it does because of the temperature that it is. So in reality, we don't have to go to the sun to figure out its temperature by sticking a thermometer in it. The light from the sun will have information that is part of that light that is related to its temperature. Wien's law allows us to take that information about the light and allow us to calculate the temperature. So we can determine the temperature of the sun just by the light that it's emitting. And in case you wanted to know, 5,800 kelvins is almost 11,000 degrees Fahrenheit. Very hot. Now, that's about all the time we have. In the next segment, I'm going to show you a couple of examples of how we can put Wien's law into practice in other ways and what it can do for us. I hope you'll join me.